Hello, everyone. I'd like to welcome you to this MacDermid Enthone discussion on the advantages of zinc nickel free phosphates. My name is Robert Collin. I'm the America's Technical Manager for MacDermid Enthone. I will be the moderator of this session. The presenter is Ron Kukura. He's our Product and Business Development Manager for surface finishing, phosphates, and hard chrome. Any and all questions you have, please put them in the questions box in this webinar, and we will answer them at the end of this session. If we can't get to your question directly, we'll send you an email as a follow-up. Again, thank you all for taking the time to learn about our nickel-free phosphate systems. And Ron, the session is all yours.
Okay, well, thank you very much, Rob, and good morning and welcome to everyone. My name is Ron Kukuro. I'm North American Product and Business Development Manager for surface finishing, phosphates, and hard chrome. And I'm pleased to have the opportunity today to share with you information regarding the MacDermid Enthone nickel-free phosphates portfolio and to look at how these products can reduce the complexity and improve the capability of the phosphate process. And the agenda that I'll follow this morning is to first take a look at the general functionality of zinc and manganese phosphates. From there, I'll take a look at MacDermid Enthone's nickel-free best-in-class products. I'll then talk about the advantages associated with our nickel-free processes. Then I'll take a look at two success stories where we have converted customers from traditional nickel catalyzed zinc phosphate systems to our nickel-free technologies. And then I'll wrap it up by taking a very brief look at some examples of the kinds of product literature that we make available to our customers. So let's begin by taking a look first at the heavy zinc phosphates. And this class of phosphates is going to be selected due to their ability to hold and retain very large amounts of top coats. And this ability is due to both the layer thickness as well as the crystal morphology of this class of zinc phosphates. And as a result of this ability, these are going to be popularly chosen in applications involving anti-corrosion, lubrication, and applications where wear reduction is required. And the anti-corrosion performance of this class of zinc phosphates is going to be variable, and it is entirely dependent on both the quality of the pretreatment as well as the coating chosen. And some examples that we can give would be if we look to the automotive industry as an example and look at heavy zinc phosphate and oil specifications. Typically, those are going to require anywhere from 24 to 168 hours of neutral salt spray performance. At an opposite extreme, if we look at the oil and gas industry and look at fasteners coated with heavy zinc phosphate and used in combination with a fluoropolymer coating, those can achieve up to 3,000 hours. So again, the anti-corrosion performance is entirely dependent both on the quality of the pretreatment as well as the coating selected. And the requirements for this class of zinc phosphate are typically going to fall within coating ranges of 1,500 to 4,000 milligrams per square foot. The calcium modified zinc phosphates are frequently used as bases for paints or other organic coatings. They're used extensively in rubber bonding applications, and we see their use in the automotive industry for coefficient of friction modification. And the effect of the calcium in these formulations is to limit the size of and effectively modify the crystal structure of the coating. And this results in a very densely packed coating consisting of very small granular looking crystals when you look at it under magnification. And it's for this reason that you'll often hear these referred to as microcrystalline processes. Now, unlike a non-calcium modified zinc phosphate, this class is going to incorporate a small amount of calcium in the layer, and this lends itself to the very desirable functional properties of this phosphate class for the applications in which they're used. Now, as I mentioned at the top of the slide, these are used frequently as bases for paints or other organic coatings. And a big reason for that is due to the chemical resistance that they have and their ability to limit corrosion spread if the coating is damaged. And you'll often hear this corrosion spread referred to as creep in the specifications. And I also mentioned at the top that this class is used extensively in rubber bonding applications, and that is because of their ability to withstand frequent and very high vibrational stress loads like those encountered in the noise and vibration isolation applications of rubber bonding. And the typical coating weight requirements for this class are going to fall within the 150 to 1100 milligram per square foot range. And because of the reduced layer thickness of this class, as well as the crystal morphology of this class, they're not nearly as absorptive as the heavy zinc phosphates. The cold forming zinc phosphates are going to be used in metal deformation applications, and I've listed several examples here. And because of the very high friction loads involved in these kinds of applications, the phosphate is going to be used in conjunction with a lubricant. And we find that these are typically formulated as nitrite or chlorate accelerated systems. And the reason for that is that these oxidizers limit the iron growth in the bath. And when we limit the iron available in the bath, we limit the amount of iron incorporated into the phosphate layer. And by limiting the iron in the phosphate layer, this results in a reduction of abrasion of the phosphate coating. And this is a desirable attribute for these phosphates for the applications in which they're used. To further address the frictional aspects, this class is often going to be used in combination with a grain refiner. And this is to create a smoother and more uniform crystal morphology, again, to create a layer that has the desirable characteristics for these high friction applications. And the coating weights for this class are typically going to be required to fall within the 300 to 2000 milligram per square foot range. The manganese phosphates are by far the hardest and most wear resistant of any of the phosphate classes. And for this reason, they are extensively used in the oil and gas industry for coating threaded couplings, fittings, and for a variety of oil rig components. They're also extensively used in the automotive industry for coating powertrain components. And the manganese phosphates are far more stable than our zinc phosphates under conditions of very high temperature and pressure. And this is due both to the chemical constituency of the manganese phosphate as well as the very densely packed cubic crystal structure of the grain refined manganese phosphate layer. Now, unlike zinc phosphates, it's really essential with manganese phosphates to use these in conjunction with a grain refiner. And this is to create both a more corrosion resistant layer and to create the wear and friction resistant crystal structure required for its high wear applications. And coating weights for the manganese phosphates are typically going to be required to fall within the 750 to 3000 milligram per square foot range. Now let's take a look at MacDermid Enthone's nickel-free best-in-class products, beginning with the zinc phosphates first and Kiko 501. And Kiko 501 is a nitrate accelerated product. It is a single component calcium modified product that is commonly used in pre-paint and rubber bonding applications. And the 501 process offers customers the flexibility to operate this as a nitrite accelerated process by using the additive Kiko 303. And when we operate Kiko 501 in this manner, it allows for a significant reduction in operating temperature of as much as 18 degrees. Kiko 514 is also a nitrate accelerated product. This is a two-component calcium modified product that is commonly used in both pre-paint and cold forming applications. And I'm a big fan of two-component zinc phosphates because of the stability and enhanced performance that they can bring to the table. Kiko 750 is once again a nitrate accelerated process. This is a two-component mid to heavy coating weight product that is commonly used in applications where either corrosion control is needed or lubrication is needed. Kiko 731ZG. This is a single component nickel-free manganese phosphate. And what we find with the 731ZG process is that it offers users, practically speaking, a reduction in complexity versus traditional nickel catalyzed products. And to illustrate that, in this slide, I show an example of some work that we did with the 731ZG process to coat a series of threaded coupons of different alloy compositions. And we purposely chose these alloys because they're often associated with difficulties in consistently obtaining coating uniformity, coating weight, and adhesion in the field. And what's noteworthy here is that we were able to achieve complete coverage, uniformity, and adhesion across all of the alloys at just 185 Fahrenheit with 10 minutes immersion and without the need to change bath parameters. And by way of contrast, typically if you were trying to phosphate these alloys using a traditional nickel catalyzed manganese phosphate process, you'd be operating at significantly higher temperatures of typically 200 to 210 degrees Fahrenheit. So with the 731ZG process, we were able to shave 15 to 25 degrees from a typical nickel catalyzed system without compromising performance, and again, without having to change bath parameters. With that, let's take a look now at the advantages associated with our nickel-free processes. And regardless of whether we're talking about nickel-free zinc phosphates or nickel-free manganese phosphates, our nickel-free phosphates operate at significantly lower temperatures of as much as 30 degrees below their nickel catalyzed counterparts. And they yield very consistent coating weights and adhesions, even on traditionally difficult to phosphate alloys, like the examples that I list here. In addition, we've designed these processes to limit the soluble iron in the bath. And what this means is that when operated properly, these baths will maintain the soluble iron within the optimum concentration range. And that optimum concentration range falls between 3 to 9 grams per liter. And what we find is that by maintaining the iron within this optimum range, it has a stabilization effect on the bath, and this results in less sludge formation in the bath. And all of these combine to translate into less maintenance required of the bath, as well as fewer bath makeups required. So with that, now let's turn our attention and look at a couple of success stories. Again, these will deal with converting customers who had been using traditional nickel catalyzed systems to our nickel-free technologies. And I'm not going to refer to the actual names of these customers. I'll merely refer to them as customer A and customer B. So let's begin by looking at customer A, who is a manufacturer of pipes and couplings. And when we met with customer A, they were dissatisfied with their current process. They were looking for ways to improve the efficiency and effectiveness of their process in several areas. And one is that they were interested in ways in which they could change the process or modify the process in order to enable them to operate at lower temperatures. And this was driven by their desire to look for operational cost savings. They were also interested in ways that they could modify the process to improve coating weight and adhesion consistency across the various alloys that they had to deal with. And that interest stemmed from their current rework rate that was fairly high. So they were looking at ways in which they could reduce their rework. And of the alloys that they had to deal with, L80 was typically their biggest challenge. And specifically, they had difficulty with consistently meeting their coating weight requirements for the L80 alloy. And finally, they were interested in ways in which they could modify the process to reduce the sludging of the bath and to reduce the frequency with which they would have to take their tanks down to desludge. And with their current process, they were having to take the tanks down to desludge at a frequency of about every 1 to 2 weeks. So they were looking at ways to expand the window before having to take down the tanks to reduce their downtime. So after a few conversations, we decided to go ahead and trial a bath of the Kiko 750 process. We chose to begin with a 7% makeup concentration and a target operating temperature window of 150 to 155 Fahrenheit. And on the day that we were there to start up the process and lend technical assistance to them, they had equipment issues such that we could not proceed. So it was mutually decided that we would go ahead and leave, and then after they had resolved the issues, they would call us back. And as it turns out, they were able to resolve their equipment issues later in the day and decided to go ahead and try their hand at starting up the 750 process without any on-site technical support. And when we arrived the next day, we were both surprised and pleased at the fact that they had been able to process several loads with satisfactory results. And the customer was happy by the fact that they were able to process with the results they had gotten using a process that they had absolutely zero experience with. So the process has now been in place for over a year at customer A, and let's take a look at a summary of the benefits that they have been able to establish during that time. So they have been able to sustain a reduced operating temperature. The previous process had operated at a temperature of 175. They have been able to reduce that to 155 with the current process. They've also been able to reduce their desludging frequency. So again, they had to take their tanks down typically every 1 to 2 weeks to desludge. We have widened that window to about every 8 to 12 weeks. And when you multiply that by the typical downtime of 6 to 8 hours, that translates into a lot of additional productive time over the course of the year. The process has also enabled them to run the alloys that they have to deal with without the need to adjust concentration or temperature. And it has eliminated the inconsistency in meeting the coating weight requirements for the L80 alloy. And finally, it has resulted in a process that delivers consistent coating uniformity and the adhesion that they expect and require across the various alloys that they have to process. And so after a year plus of being in place, the 750 process has resulted in positive changes for customer A and resulted in a robust process. And now let's take a look at customer B. And customer B is a manufacturer of drilling tubulars and accessories. And we met with customer B to discuss their current process and issues that they were having. And they had two primary technical challenges. And the first is that they were unable to consistently meet their coating weights across the alloys that they had to deal with. And to try to combat this, they extended the immersion time to 45 minutes. And 45 minutes is an exceedingly long immersion time. In addition to that, they had an issue with inconsistent adhesion, and this was increasing the rework that they were having to deal with, and then obviously increasing their operating costs. So after several conversations, we decided to go ahead and trial a bath of Kiko 750 at their plant. At one of two plants. If we were successful at one, we would go ahead and roll the process out to the second. Here again, we decided to start with a 7% makeup and an operating temperature window of 150 to 155 Fahrenheit. And we decided to dramatically decrease the immersion time from the 45 minutes that they had been using with their previous process down to just 15 minutes, and then we would adjust as needed. So the 750 process has now been in place for a year at customer B. And so let's take a look at the process benefits that we've been able to establish in that period of time for customer B. So they have sustained the reduced immersion time. The previous immersion time, again, had been 45 minutes. We've reduced that to 15 minutes. And that additional 30 minutes over the course of a year represents a lot of additional productive time for the customer. In addition, they've been able to sustain a reduced temperature. Their previous process operated at 175 Fahrenheit. We've dropped that to 155. So again, this 20-degree differential over the course of a year represents additional cost savings. The process has enabled them to consistently meet both their coating weight and adhesion requirements across the various alloys that they have to process. And it has reduced the desludging frequency. They had been having to desludge at a frequency of about every 2 weeks. This has been extended out to 6+ weeks. And it has resulted in a process that enables them to use a single process for all of the alloys that they have to process without the need to adjust bath parameters. So after being in place for a year at customer B, the 750 process has resulted in a reliable and robust process for customer B. And now I'll take a brief look at examples of product education literature that we make available to our customers. And these product-specific brochures that give a lot of nice general information about the product, as well as to look at key features associated with the product and ways in which you can modify the process to enable to meet different aspects and requirements when using the product. It also outlines a best-in-class process sequence for a given product. And another aspect that I really like about these is that it includes all of the specifications that a given product will meet. We then have more general brochures like this that take a look at the various applications that the phosphate portfolio will meet. Takes a look at the core products and core products of the product line, and then typically we'll have a technical section. And in this example, we look at the effects of dissolved iron in the phosphate bath solution in order to maintain optimum process efficiency when using the product. And then finally, we have these more in-depth articles, such as this example for Kiko 400, which is our best-in-class dephosphating chemistry. And so with that, I would like to thank you all for sharing a part of your day with me. And I hope that you all stay healthy and well as we continue to navigate this unprecedented time.
Thank you, Ron. Great session on the advantages of the nickel-free phosphates that are offered. There are a couple questions I have sent you in your email. If you can take a look
Okay.
and answer as needed, that'd be great.
All right, great. Let me take a look. Okay, so basically I've got a couple of questions, as you point out, Rob. The first is asking what the typical salt spray life of a Kiko phosphate coating is. And, you know, as I pointed out during the presentation, it is really impossible to assign a single value to that. And that is because it is going to vary on the type of phosphate that we're using. And if we take a look at the zinc phosphates as an example, a heavy zinc phosphate is going to have, because of its layer thickness and the crystal morphology of that class of zinc phosphates, is going to be able to hold and retain a much higher level of dry to touch oils or other anti-corrosion oils, and therefore it is going to have a much longer anti-corrosion life. So in other words, we'll be able to attain many more hours of neutral salt spray with a heavy zinc phosphate than we could with, say, a thin microcrystalline layer, which, because of the reduced thickness of that layer as well as the crystal morphology, and they really, there's two effects there. The thickness and the crystal morphology, they are not going to be able to hold and retain an anti-corrosion oil to the same degree, and so they are not going to have the same level of anti-corrosion performance and are not going to be able to get as many hours, for example, of neutral salt spray performance. The other component that I talked about that's very important here is the type of coating that we're using in conjunction with the phosphate. So, you know, again, on the automotive side, if you look at heavy zinc phosphate and oil specifications, that is, you know, those typically span 24 to 168 hours. If we look at using a heavy zinc phosphate in combination with a fluoropolymer coating, like we see in the oil and gas industry, those can attain nearly 3,000 hours. So again, I know this is a long answer to your question, but you really can't assign a specific value to the salt spray life of the coating because of the variables involved. So I hope that answers your question. And then I have another question here of what is sludging and phosphating? Well, it is a falling out of, I'll just in general terms, of material from the phosphate bath. And typically these materials are very iron rich. And so these will fall out just as a matter of course during the phosphating process, and will accumulate in the bottom of the tank and accumulate on the tank walls and so on and so forth. And it is imperative that you remove this sludge periodically, because if you don't, it will adversely affect the entire process. It will adversely affect the composition of the bath, as well as the fact that if you have a lot of sludge in your tank, this sludge can find its way back onto the parts and interfere with the phosphating process. So I hope that answers your question. And so, Rob, that is all of the questions that I received.
That was great, Ron. Thanks again. And again, if you need any additional information, please email Ron Kukuro directly. He will get back to you with to start your discussion. Anyway, that is the end of this session. We hope within a week or so, these materials will be available on our website. And again, thank you very much. Enjoy your day. Everybody be safe.